All right, students, let me help you with another one from Chapter 5 in the Universal Law of Gravity. It says, if an astronaut in full gear weighs 1,200 newtons on the Earth, how much will the astronaut weigh on the moon? Okay, well, again, this chapter is all about what we call the universal law of gravity. And you just take your two objects and the distance between them and put it in this little formula here, and you calculate how much that force is. So if the object is, say, U and the Earth, that would be the weight of U. If it is a car and the Earth, it would be the weight of the car. Now, if you go to another planet, or in this case a moon, then you ask how much do you weigh on the moon, it would be between you and the moon here. So that's going to be my numbers here, my calculation, if you will. And so I need to know then something like, well, let me draw a picture. If here's the moon, I would need to know, okay, what is the radius here of the moon, because I'm going to be standing here on the moon. And of course, that distance between the center of me and the center of the moon, the radius of the moon, is essentially the number that goes there. How far apart are our centers? And then I would need the mass of me, and I would need the mass of the moon. Okay, let me start with the one that they help us get. That would be the mass of me. In fact, maybe I should just remind you, weight is mg. That goes back a chapter or two. And so they gave us a helpful hint, because they're saying that the weight of the astronaut on the Earth, so the weight of the astronaut on the Earth, the 1,200, is of course the mass. And I think it said all the gear. Let me look here. It says, excuse me, an astronaut, in full gear. So this is more than just the weight of the astronaut, but the astronaut and all the gear is 1,200 newtons. And so this would be the mass of the astronaut and all the gear times roughly 10, and maybe I should put meters per second squared, so that when I divide here, I've got a 1,200 divided by a 10 and a newton divided by a meter per second squared. And just as a reminder then, a newton, I'll put it up here, is a kilogram times a meter per second squared. So the meter per second squared on the bottom would cancel with those on the top, leaving the appropriate units of kilograms. And then, of course, 1,200 divided by 10 is 120 kilograms. So that information is very useful, and it's part of the problem. It is, how much mass do I have? Okay, fine. Now, the other part of this really is going to require you to look it up. It's listed in the book. I have a little chart here. I'm going to grab my chart. It's all right, over on the bookshelf here. But it lists all kinds of useful information. But just Google it. By the way, you might call an easy way to do this, but I don't think this is what the author wants. He did say in the book here that the force of gravity is 1/6. So I suppose I could have just done this problem and said, well, okay, you're 1,200 newtons on the Earth, and if you divide that by 6, you get 200 newtons. Yay! But that's not really, I think, the intent of this physics problem. The intent is to actually do the universal law of gravity. So let's see what I get here. Okay, so I'll put in the G, 6.67 times 10 to the negative 11, and the units are a newton and then a meter squared and a kilogram squared. So let me use this as another example to say, make sure you put then your masses in kilograms and your distance in meters, okay? So I need to put in the mass of the first object. Let me call that the moon. So if I'm trying to find my weight on the moon, the two objects would be the moon and me. Or not me this time, the astronaut, so 1,200. In fact, maybe I'll just put that right here. Sorry, 120. So we figured out earlier that the mass of the astronaut and all the gear is 120 kilograms. Okay, but the moon we need to look up here, and so it says somewhere here that the mass of the moon is 7.36 times 10 to the 22 kilograms. Okay. Then if we divide that by the radius of the moon, so the same chart lists not only the mass but the radius, 1.74 times 10 to the 6th meters. And let me point out again, you got to make sure your distance is in meters. All right, so we would have kilograms cancel with kilograms. Okay, good. And then we would have meters squared cancels, and then that's actually a meter squared. Okay, so we're left with units of newtons. Good, because that's what we want. So now we can punch in our numbers here. So grabbing my calculator, 6.67 times, whoops, I guess I turn it on. So 6.67 times 10 to the negative 11 times the mass of the Earth, 7.36 times 10 to the 22, times the 120, then divide by the 1.74, times 10 to the 6th, and square that, and hit enter. And it looks like I'm getting 195 newtons. And so pretty close to the rough number that they said in the reading, just to it's about 1/6. And so it looks like it's a little less than 1/6. Very close to 1/6, but a little bit less. So there it is. There is how much you would weigh on the moon. Or not you, the astronaut and all the gear that makes up the astronaut's life support system. All right, hope that helped.